Hi, this is the first lecture for frequency response. What does it mean, frequency response? Let's assume that we have a linear network represented by this box. And we have input. Let's say this input is equal to x of t, and we have output, and the output is equal to y of t. And let's assume that the input is a function of time and frequency, and the frequency of the input changes. Like what? Like if you can say x of t is equal x maximum cosine omega t plus theta. And we like to change the omega of the input. We'll keep this constant, the amplitude constant, and we'll change the frequency, and then we wish to find the response of the system. We wish to find the output response to the change of the frequency of the input. That means frequency response. Well, to do that, you got to change all variables here into frequency domain. So just to sketch again the same linear network, and the input will be x capital of omega, not of time, and the output will be y capital of omega. And there will be a transfer function, we call it h of omega, because it depends on the frequency, and it's the ratio between the output, y of omega, divided by the input, x of omega. That's called transfer function. So the transfer function relates the output to the input. And you can express transfer function in general in a rational function, numerator, that's a polynomial, function of omega, denominator, function of omega. If you wish to find the roots of each polynomial, so you set numerator to equal to 0 and find the roots of this equation or this polynomial. The roots will be called zeros. And if you want to find the roots of the denominator, you set it equal to 0 and find the roots, and the roots will be called poles. Great. Well, we like to study the frequency response of a simple circuit. So let's take an example. This example will be simple RC circuit. So we have R and C and input. And that's the input, the source, and that's the output, the V output of time. Let's assume that the input is equal to V maximum cosine omega t. And we like to find the output when we change the omega. So we sketch again the circuit in frequency domain, and we express everything in phasor. So that will be Vs of omega, and Vs of omega defined as the maximum voltage and angle 0 or theta. In this case, just let's take it at 0. The resistance stay the same, and the capacitor will be 1 over j omega c, that's ZC, and the output will be V output capital of omega. By the way, in frequency domain, we use the capital letters to express the variables. Well, in this case, we can find the transfer function, which is equal to the output by the input. Well, How can you find the relationship between the output and the input? You can use voltage division. So the output VO will be equal VS times ZC over the total impedance R plus ZC. So let's just go ahead and do it. That will be equal to ZC divided by ZC plus R. ZC is equal 1 over J omega C. 1 over J omega C plus R. That's the transfer function. Relates the output to the input. Let's simplify this expression. Okay. I'll multiply in the top and the bottom by J omega C. So you have 1 over 1 plus J omega R C. So that would be the function, the transfer function, which relate the output to the input. That's the first requirement. Well, the objective is not just to write the equation for the transfer function. The objective is to find how the frequency affect the output amplitude and the output phase. That's our concern. So we need to find the magnitude of H and the phase of H. So there are always two parameters that we are interested in to analyze. The first one is the magnitude, and you might call it H, which is mean the magnitude of the transfer function itself, and the phase. Let me just write here the magnitude so you know what to talk about. And the second part, we need to find the change of the phase, the effect on the phase of the output. We call it phi, and that's equal to the angle of the transfer function. So always we have two main parts to understand the transfer function of any circuit in the frequency domain. All right, let's first check the magnitude, and we're going to use the transfer function here. So I will write it again. I will say that H was given as 1 over 1 plus J omega RC. And let's just take some assumption here. Let's call that omega naught equal to 1 over RC. We'll call 1 over RC omega naught. So our equation now can be simplified as 1 over 1 plus J omega over omega naught. That's the new form of the transfer function. All right. Now I want to find the magnitude, which is called H. H is the magnitude of the transfer function. So it will be equal 1 over, and the magnitude on the bottom, square the real, the imaginary, and that will be the amplitude. Good. So I want to see or study the magnitude of H, how it changes when I change omega. Remember, this omega is the frequency of the supply, but omega naught is constant, depends on RC value, the parameter of the circuit. I will take value. I will say, okay, if I put omega here, I make a simple table. I'll say, okay, omega. I'm going to take just simple values just to get feeling of the change. That's omega, and that's the magnitude. Well, I will take if omega equals 0. So what you get? Well, when omega is equal 0 in this equation, so you will have H equal 1 over 1 square plus 0 square root. So you have 0 plus 1 will be equal 1, so it'll be 1 over 1, which is equal 1. So h will be equal 1. Okay. What about if omega equal omega naught? When omega is equal omega naught here, so h will be equal to 1 over square root of 1 square is equal 1 plus omega equal omega naught to be 1 also. 1 square will be equal 1, so it will be 1 over square root of 2, which equal to 0.707. So h will be equal to 0.707. Let's take a big value. Omega is equal infinity. When omega equal infinity, let's just here's these values. When omega equal infinity, h will be equal to 1 over 1 square plus infinity square. So it's equal 1 over infinity, it's equal 0 again. So I just got very simple. Let's just sketch now h magnitude against omega. So you have y-axis, x-axis, which is omega, and here the magnitude h. Started when omega equals 0, the value is equal 1. And it start to decrease from 1.707, 0 starting, so it will be like till to get 0 when omega goes toward infinity. But at omega naught, the value is equal 0.707. This omega naught is called cut off frequency. Well, let's just study what does it mean, this curve. It means when omega equals 0, h is equal 1. And what's h? H is the relationship between the output voltage and the input voltage, the magnitude. When you say it's equal 1, it means that the output voltage magnitude will be equal to the input when omega equals 0. What does it mean, omega equals 0? It means DC component. DC component, something like that. So if you have input equal 12 voltage, the output will be the same, 12 voltage. So this circuit will allow DC to pass through the circuit and no attenuation happen to the amplitude. Great. And every time you have signal with frequency higher than DC, the amplitude start to decrease till you reach omega naught. So if you have sinusoidal wave with frequency equal to omega naught, and if the amplitude is equal, say 100, that's the input, you'll find that the output will be the same, but the amplitude will be less, will be 0.707 times the input, because this is h. So you will have the output 70.7 voltage. So it have an attenuation, okay, by this value. And every time you increase till you get high frequency, something like that, high frequency, so you'll find the amplitude is really very small at the output. So this circuit that we just explained, it just behaves as a low pass filter. It means it allow any input with low frequency component to pass through, but any input with high frequency will be attenuated, will get smaller amplitude. To what frequency? Well, till omega naught, the cutoff frequency. Because at the cut frequency, the amplitude will be reduced to 0.707. If it reduced, or if you have frequency higher than that, omega naught, so the amplitude will be decreasing dramatically. It will not be strong signal anymore. Okay, that's about the amplitude. What about the phase? Well, let's just write the equation again. See what happened to the phase. H for omega is equal 1 over 1 plus j omega over omega naught. The phase phi is equal the phase of the function h. The top part is 1, so the angle is equal 0, minus the angle of this one will be tan minus 1 real, imaginary over the real, so it will be omega over omega naught over 1 will be omega over naught. So in general, you can say that phi is equal minus tan minus 1 omega over omega naught. We'll make the same table as we did last time. We'll say that's omega and that's phi. And we'll choose some values when omega equals 0. So you want to find minus tan minus 1, 0. That's equal 0. When omega is equal omega naught, so you have minus tan minus 1, 1. Tan minus 1, it gives you 45, and you have the negative sign, so it will be minus or negative 45. When you have infinity, you know that tan minus 1 infinity is equal 90, and you get negative sign here, so it will be a negative sign. So what's happened here, the frequency will increasing, then phi decreasing from 0 up to negative 90. So let's just go ahead and sketch the phase. That's omega, and that's the phase. That's 0, and that's negative 45, and that's negative 90. In the end, it will go to negative 90 and go to infinity at omega naught. The value is equal, so it will be just decreasing like that till it get to negative 90. So that's the effect of the phase. It means when you have DC component, there is no shift. Of course, it doesn't have anything, but every time you are increasing the frequency of the input, there will be shift. What does it mean, shift? Let's say at omega naught, if you have a sine wave like that as input, and the magnitude is equal 100, and starting from 0, so the equation will be Vs of t is equal 100 sine, and the frequency equal omega naught t, and let's stay starting from 0. It will have a shift negative 45. What does it mean? It means that the output, the amplitude will be less, as you know, will be 70.7, and it will not start from 0. It will be delayed by 45. So at 45, the sine will start. So that's the meaning, the effect of the phase. It will not start, then you can continue to make the sine wave. So it means it's shifted, delayed by 45 degrees. And you so go ahead till the frequency is getting higher, the amplitude will decrease dramatically, and it will be shifted by minus 90 degrees. So that's the frequency response of a system. I hope it was helpful. Thank you.